The mathematical calculation of the electric dipole field. Let's sketch the geometry of the situation. So the configuration is that we have two dipoles, and let's say that the dipoles are going to look something like this. So I'm going to say that here's one of the charges. Then I'm going to have my second charge, let's say right here. And what we find here is that it's customary to pick the origin to be in the middle of the two dipoles. So I'm going to pick this point right here, and I'm going to call that my origin. So I'm going to say that's z equal to 0. So then I'm going to pick an observation point, and let's say that I picked my observation point P right here. And so what do we expect? Well, there are two distances that we should think about. There's the distance of the positive charge that goes from here to there. And then there's the distance from the negative charge that goes from here to here. And so when I start to look at the distance between the charges, we've already defined that to be d. So then the separation between here and here is 1/2 d, and the separation between here and here is 1/2 d. So that's going to be super important to how we write down the displacement vector. So now, if I look at superposition, what am I seeing here? You can see here is that the red displacement is smaller, so therefore it's going to have a larger field. The green displacement is larger, so I'm going to have a smaller one. So when I look at those fields, I expect the positive field to be larger than the negative field. Therefore, I have a dipole field right here, which is, of course, due to superposition here. So now, what do we know about what we have here? So we've already said that we could say that the configuration shows that one, the positive charge is closer than the negative. So then I'm seeing here is that E positive is then going to be greater than E minus, just as expected, and R negative, which is farther away, has to be larger than R positive. The other thing that we should see here is that if I look at the displacements, the displacement of the charges are as follows here. So if I look at R plus, you could see that it's, so I gotta, you know what? I didn't define one thing. I realized I did not find the distance from the origin right here, from here to here, I'm gonna call Z. So if I look at the positive displacement, that should be Z minus 1/2 D. If I look at the negative displacement, that should be Z plus 1/2 T. So now I have my displacements here. And that's a big part of the problem solving. So we have superposition, which shows up right away. So now, using superposition, the magnitude of the net field we define as the dipole field is as follows. It says that I have a dipole field and that dipole field is equal to the red field minus the negative green field. And so now I just start putting them together. So I'm going to get 4 pi epsilon. They both have the same charge. So this would be 1 divided by r plus squared minus 4 plus epsilon divided by r minus squared. And if I put in the displacement values, you'll see here is that I get a dipole field that now reads like this. I have 4 pi epsilon into q, and I'm going to get z minus 1 half d squared minus z plus 1 half d squared. And this right here is my field equation for the dipole. So I now have my field equation. This is what we wanted. Now, if you look at this thing, we can clearly say this field equation solution is ugly, but it makes physical sense. And let's go through this. So the first thing that you should note is that we have two denominators, that the two denominators each have a singularity at z equal to plus and minus 1 half d. That is, the dipole field goes to infinity at these points. That's what I mean by singularity. However, we really don't care about z equal to minus 1 half d, because the way of the geometry is you're seeing that we're outside the physical dipole. So we only care about what happens above z greater than 0. So I should come back here and say here is that because of the way the problem is set up, we only care about Z greater than 0. Let's go look at that now. So there's an issue here. So why is there singularity? So now let's look at the configuration. So as point P approaches the positive charge, the field increases to infinity. And what I mean by that is that if I look at my dipole charge, and let's say that this is it right here, and this is my point P. So now I'm going to look at this thing in the limit as Z approaches positive 1/2 d. Now remember, this is what we called Z equal to 0, and this is the distance positive 1/2 d. We can clearly see that as I approach a point charge, that field has to go to infinity. So the same thing happens with the dipole. So if I take a limit as Z approaches plus 1/2 d of the dipole field, what we're seeing here is that we're really taking this limit right here. We're taking the limit, and if I look at the denominator of the first term, this is Z minus 1/2 d squared, and then there's this second term, which really doesn't mean very much as far as the limit is concerned. But here, you're seeing that this term goes to infinity. And because it goes to infinity, that's a big problem, right? That's a big red flag that something has gone wrong in physics. So we've already discussed this. As Z goes to plus 1/2 d, Coulomb's law is not valid anymore. To be able to continue to use Coulomb's law, we must avoid those singularity points. So if I start to plot this thing, what am I actually seeing here? So I'm going to plot. So I want to plot E dipole versus Z, where Z is always greater than 1/2 d. So there's a strong singularity. So we are outside of the physical dipole and we're not near. So what do we see here? So I'm looking at this guy. So note that there's two singularities, and I'm only focusing on one. So if I was to plot E dipole, what we're going to see here is that at one point here, this is where Z is equal to 1/2 D. So we know that field goes to infinity here. So this is the location of the positive charge of the dipole field. So if I was to say, well, I mean, I really can't ignore it, but this would be also the negative part of the dipole. And again, if I look at this distance from here to here, that's 1/2 D. And from here to here, that's 1/2 D, just as the problem shows. So now what you're seeing here is that picture-wise, I'm going to see a field that's going to look like this. So what am I seeing here? The first thing that we should pay attention is that right here, we say here is that Coulomb's law is not valid. So we stay away from that point. The other point that you really want to think about is this guy right here. Look at right here. In this situation, we're seeing that in the limit, as Z approaches infinity, that field of the dipole, of course, goes to zero. All fields go to zero. So the only point we can analyze is that we're going to say that we want to look at points probably somewhere around here. So we're gonna look at a dipole field that is far enough, and what we mean by far enough is that Z is much greater to have a non-zero field. At infinity, it goes to zero, but we don't care about that. So now to put this into a sentence or so. So to understand some dipole characteristic, we will look at point Z much greater than the charge separation. Once again, if we're close to the dipole, we got to use that other equation, which is not nice. So that's not going to help us. So now, here we go. Question. What is the field equation behavior when Z is much bigger than D? That's what we've been looking at. So mathematically, this seems a fairly easy thing to do. Mathematically, it seems straightforward to calculate the field equation when Z is much, much bigger than D. Let's just look at the equation, right? So if I look at the limit, and I'm just going to say that Z is much, much greater than D of the E field of the dipole, I'm really saying that this is going to be 4 pi epsilon Q, and then I'm going to take the limit as Z is much, much bigger than D. Well, I have two terms. I have Z minus 1/2 D squared minus Z plus 1/2 D squared. And so when I look at this, well, if Z is much, much bigger than D, then clearly we can just ignore. The same thing happens over here. We can just ignore it. But if I do that, look what happens. This tells me that this approximation says that 4 pi epsilon Q, now I'm going to get an expression that reads 1 over Z squared minus 1 over Z squared, and that's equal to 0. But wait a minute. Only at infinity is it 0. It's not 0 there. So the only conclusion we could say here is this is incorrect. So it's not so easy to just mathematically just start throwing in terms. So the reason why this gave such a wacky answer is it was done incorrectly. It was done incorrectly. And that's what I call the lazy person's method. So let's list this thing here. So the first thing that we should do is we should say that what we just did is the lazy person's method, which, in just simple language, you did it the cheap way. You didn't want to put the work in. So in this process, one immediately applies Z much, much greater than D and hopes for the best. It turns out that most of the time it works out great, but not all the time. So what is the method that always works? We do a Taylor series expansion. And what do I call this? So when I do that, what we have to do here is that we set up a Taylor expansion that always leads to the correct answer. If the series converges. So we need that to happen, but we only deal with nice functions. So probably the most common one that we use here is the binomial expansion. So one very useful expansion is the binomial. And it's written numerous ways. So one very useful expansion is the binomial that works well with electric fields as well as magnetic fields. It turns out that many field equations have power function forms in their denominator that can be rewritten into a form that says that if the electric field is a position of is dependent on the variable x, then this guy will then be proportional to 1 plus x to the n. And this is only valid. So if I do a Taylor expansion, what we have to make certain that this is the case is that this value x must be very small. If it's not small, we can't do an expansion. So here's what we say. The binomial expansion, which I typically call an approximation, is only valid if x is much, much smaller than 1, where in the limit, as x is much, much smaller than 1 of this function, then equals 1 plus nx plus n minus 1, 2 factorial x squared, and then I get all of these higher order terms. So it turns out that, in general, higher order terms are extremely small and ignored. That tells me that we then have this guy, that if I take the limit as x is much, much smaller than 1 of this power function, we can approximate this as 1 plus nx. This is what I call the binomial approximation. To apply the binomial expansion or approximation, one has to prepare the field equation to match the binomial form. And this is the trickiest part, without a doubt. So let's do this now, and let's go through steps because this is tricky. So ultimately, what we want to do is that we want to apply this to the electric dipole field and see where we're at. So let's do this in steps. So we'll start with step 1. So here, we need to set up our expansion parameter. That is that if z is much, much greater than d, then this is the same as writing d over z, which is now defined as x. That's going to be much smaller than 1. If you ever hear me say this, this is the expansion parameter. And that might be the hardest thing to see, even though it seems fairly straightforward. It's not. So then if we go to step 2, we need to rewrite the dipole field equation into proper binomial form. So if I look at the equation for the dipole, it looks like this. So to put it into proper form, we have to create a parameter that's d over z. So when I'm looking at the denominators, we have z minus 1/2 d squared, and then I get z plus 1/2 d squared. So in order to create d over z, we have to factor out z in both of the denominators. So if I do that, then look what I find. I get 4 pi epsilon into q. So if I factor out a z of the first one, I'm going to get a z squared. But now I get a term that's 1 minus d over 2z squared. And now you're starting to see that power function that we were talking about. And I do the same thing with the second term. And I get 1 plus d over 2z squared. So now if I clean this up a little bit, I factor out the z squared and I get 4 pi epsilon. And look at that, here's my z squared. And you're going to immediately realize that this right here is, this is the electric field of a point charge. We haven't even touched the bracket terms, but now to put it into that proper form, I need to put this into the numerator, which will then be 1 minus d over z to the minus 2 minus 1 plus d, I forgot a 2, of 2z to, so now this is in proper form. So there's two things that I can actually say right here. So if I look at this guy, what do I see here? The first thing that I see is that this bracket term separates or differentiates between E point versus E dipole, because the other term is the other one. And the other thing that you should think about here is that this is what I would call proper binomial form. So now that I have it in this form, I could now apply the binomial expansion. So now we're at step 3. Now let's take the two power functions and apply the binomial approximation. So if I look at the first term in the bracket, here's what I see. In the limit as d over z is much, much smaller than 1, I have this bracket term that reads 1 minus d over 2z to the minus 2. Now, comparing this to the binomial expansion, this sets that n is equal to minus 2 and that x is equal to minus d over 2z. So then I can approximate this by 1 plus nx, which translating this will be 1 minus 2 times the quantity minus d over 2z, and that's going to give me 1 plus d over z. That's what the approximation does. And now I'm going to repeat this with the second term. So since it's so similar, I'm just going to copy this and paste it. So instead of the first term, this will be the second term. So this is the second term. And so guess what? This is plus. So if that's plus, that's plus. This is plus. So then this becomes minus. Now what we do here is that we put this all together. And this will be now step 4. So now we're going to put everything together, and we then find that in the limit as d over z is much, much smaller than 1, E dipole can now be approximated to 4 pi epsilon z squared into q, and then I get two terms, 1 plus d over z minus 1 minus d over z. And when the dust settles, this is what we get. We get a term that then reads 4 pi epsilon z squared q. And then this guy right here, as we've already said here, that is the electric field of a point. The bracketed term is what separates this from a point, and that is 2d divided by z. So this, what I would say here is that this is the factor that separates it into a dipole field equation. So in summary, we could then say that E dipole if we could say D, I'm going to say that Z is greater than D, is then can be approximated to be 4 pi epsilon Z cubed divided by 2QD. Now this is much cleaner than the actual equation. So now our job here is to interpret this thing. Of the dipole field equation. So 1, if the observation point P is close to the dipole, then one must use that E of the dipole is this ugly expression that we derived. And again, this equation has some intuitive, where Coulomb's law breaks down at plus or minus d over 2, but other than that, it really does not help you very much. However, in the limit z much, much greater than d, the dipole, by appearance, may look point-like, but does not behave this way. There's a clear separation. And what we're seeing here is that in the limit, as z gets much, much bigger than d of the dipole, we can approximate this as 4 pi epsilon z cubed times 2qd. So it behaves as 1 over z cubed, not z squared like a point charge. 2. Our initial intuitive assessment showed that E of a point field was larger than E of a dipole field. In other words, we saw this, that E of a point is equal to 4 pi epsilon z squared over q, which of course is proportional to 1 over z squared. And then if I looked at the dipole, and remember, this only makes sense if we're far away from the physical dipole, that this guy, we could approximate this to be 4 pi epsilon z cubed, not squared, that this was proportional to 1 over z cubed. In other words, we have a stronger field strength here, and then over here we have a weaker field strength, which is exactly what we showed here. So to sort of end this discussion here, let me show you this. Numerically, I know it's easy to not really pay attention to these algebraic equations, but let's think about it the following way. Numerically, what does this mean? Well, we're saying that the point charge is stronger than the dipole, but can we look at this numerically to see what we mean by that? So if I look at E of a point, we clearly see that this is proportional to 1 over z squared. Now what I'm going to do in each case here, I'm going to double the distance. And then I want to repeat the same thing here. So if I just copy this and then modify this slightly, we can see here is that in this situation, it's not a point anymore. We're going to look at a dipole, and it's not squared anymore, it's cubed. So if I repeat this process here, I'm going to get that if I double the distance, I'm going to get 2z over 1, and that tells me that it's 4 times z squared over 1. That tells me that the field falls off by a factor of 4. But what about the dipole field? Well, this is the same as 2z, but this is cubed, which is now 8z cubed. So this tells us that the field falls off by a factor of 8. So it's falling off a lot faster. So then picture-wise, we'll say that the last thing that we want to do here is that if we plot both fields on the same plot, here's what we're going to find. So I have a field here, and I'm going to pay attention to, so when I look at the electric field, and this is my separation, excuse me, my position D, I'm going to say that this point is 0. So if I go to a point charge, this guy goes to infinity and at 0, and then it dies off to 0 right here. So I'm going to say that this field right here shows me that this is the electric field of a point. Now, if I set up a point here in the dipole field, where this is 1/2 d, you're going to see that this guy that has a singularity, not at 0, but at what this here, but then this guy falls off faster and then goes to 0 faster. So this guy right here is E of the dipole. So if I look at my numbers, 1 being 4 and 1 being 8, if I was to compare them to the same points, sort of like this point right here, I'm going to say if this point right here of the field, from the original one, that's going to be a fourth, then this guy has to be 1/8. And of course, all fields at z equals to infinity, all fields go to 0.